Welcome to this module. Here we are going to discuss some particular properties of subsequences. In the last module, you have seen how a subsequence can be defined and how a subsequence can be represented. And here we start with a theorem. That theorem states that every sequence of real numbers has a monotone subsequence, right. So, let us start with this theorem. Every real sequence has a monotone subsequence. That is, it can be a monotonic increasing subsequence or it can be a monotonic decreasing subsequence, but any sequence will have either a monotonic increasing sequence or a subsequence or a monotonic decreasing subsequence. This is for sure. Okay. To prove this particular theorem, we need to define a concept called peak. Okay. How we define a peak? Define the mth term of a sequence xn as a peak if xm is greater than equal to xn for all n greater than equal to m. What does it mean? Let us try to visualize this situation. So, I can plot a sequence, the members of a sequence like this, where these are all natural numbers, and on this side there will be real numbers, which are actually x1, x2, x3 of the sequence. Say, suppose this is 1, this is 2, this is 3, 4, and so forth. And I can take this can be x1, I can take this to be x2, I can take this to be x3, this to be x4, say this is 5, this is 6, and you can see this is x6, something like that. You can see on the right of 4, that is x4, everything is less than x4. Therefore, x4 is a peak. But under the same argument, because x3 on the right of x3, x4 is something which is greater than x3. So, x3 can never be a peak. x4 is a peak, but x3 can never be a peak. Again, from this diagram you can see x2, on the right of x2 everything is smaller than x2, and therefore, this is again a peak, and similarly this is again a peak, right. So, a peak to be a peak, xm to be a peak, you need to have all the xn's on the right of xm should be smaller than equal to xm. That is the definition of a peak. So, two observations we can have. Suppose a sequence is monotonic decreasing for a monotonic decreasing sequence every term is a peak, because in a monotonic decreasing sequence something like this will happen. So, on the right of every term will be smaller or equal to that term. Therefore, every member or every term in that sequence is a peak. But whereas for a monotonic increasing sequence, so in a monotonic increasing sequence you can have something like this, and then this there cannot be any peak, because on the right of every term whatever comes up, that is greater than equal to that term, and therefore no peak exists, right. So, these are two special cases of existence or non-existence of the peak. In a monotonic decreasing sequence every term is a peak, whereas in a monotonic increasing sequence there is no peak. Okay. Now, here coming back to the proof of this theorem, where we have to show that every real sequence has a monotonic subsequence, we are going to use this concept of peak. Now, suppose there is a sequence, let x n be a sequence of real numbers. The following two cases arise. The case 1, let x n have infinitely many peaks. It is possible. So, suppose if we want to visualize again, suppose x n has infinitely many peaks. This is one peak, suppose the next one is not a peak, maybe the second peak will be this, the next one may not be a peak, the next one may not be a peak, but this next one can be a peak, and so that you can have something like this, and it goes on like this, and then it will be having, in this particular situation, it will be having infinitely many such peaks. Okay. Suppose that is our case, then what happens? We can collect these peaks. We can collect these peaks, and by increasing their subscripts, we can represent these peaks as say xn1, xn2, xn3, xn4 and so on and so forth, such that definitely n1 is less than n2, less than n3, less than n4, less than and so on and so forth, somewhere nk, and again it goes up to infinity, because there are infinitely many peaks we have taken. Since each of these terms is a peak, since each of these terms is a peak, therefore this sequence can have this form and so on and so forth. And so, this is the required decreasing subsequence. This is the required decreasing subsequence. Let us come to the other case. What is that? Case 2. Now, suppose xn has only finitely many peaks. Let xn have only finitely many peaks. Finitely many peaks means it may not have any peaks also. Therefore, we should mention it or no peaks. It is included, but to be more precise, I am writing it or no peaks. Let these peaks be put in an increasing order of the subscripts. Because this time we have only finitely many peaks, let us put them this way: xn2, ultimately xnr, such that n1 is less than n2, less than n3, so on. Finally, it is less than nr. Now take this this natural number S1, which is equal to nr plus 1, the next natural number after nr. This is the first index beyond the last peak, Now, these are the only peaks, therefore, xs1 cannot be a peak. Therefore, there exists another index S2, which is greater than S1, such that x S2 is greater than equal to x S1. right. But again under the same argument, S x S2 is also not a peak. There exists some S3 which is greater than S2, which is greater than S1 already, such that x S3 is greater than equal to x S2 is greater than x S1. But again, since x S3 is not a peak, you can always find out another term in the sequence x S4 which is greater than equal to this term. The process continues, and we get n increasing subsequence of the original sequence. Okay. Original sequence was xn, so original sequence xn, and this gives me the existence of a monotone subsequence from any real sequence. This completes the proof.